Assalamu alaikum, everyone, and welcome to the first reading session, hosted by me, Shirif Mohammed Wael, where we will discover together the story of model-based reinforcement learning. I will explain in a bit why this topic specifically. However, I would like first to introduce myself. Who am I? I'm Shirif Mohammed Wael, fourth-year AI student at AZ Algiers, and I am the current leader of School of AI Algiers, which is the first and the largest AI community in Algeria. And what are basically reading sessions? They are the sessions where we will discover the latest research in AI in its different fields. Sometimes we invite researchers or engineers to talk about their current topics, or or whenever like we have a research question or an interesting paper to read, we can do it together. And the format is flexible. It can be through a presentation, like I am doing, like I will do today. It can be through like code work through a specific paper. It can be through reading a paper or a book. It's so flexible, and basically, it's up to our community to decide on how to drive it further. Okay, the outline or what we will see today. Before I explain what we will see, I would like to talk specifically about why exactly model-based reinforcement learning is the, the topic that I wanted to speak about first. It's because I'm currently exploring this domain, and it's so interesting. Second, because it's one of the domains in AI in general that has driven a specific revolution in AI. I think many people, even those who are not in engineering, have heard before about AlphaGo or AlphaZero, the AI model that beat the world champions in a very complicated game, which is Go. Many people have heard about such AIs that beat world champions in chess and complicated games like Dota. And model-based reinforcement learning is specifically the domain that has given birth to such powerful models. Okay, sorry. Okay, that's basically the motivation and why I wanted to start with this topic. And in order to discover such topic, we need to revise the background together. What's reinforcement learning in short, and what are its different components? Then we will discover together what's exactly model-based reinforcement learning, what's planning, and how does it happen. Then we will discover a very important component in in model-based RL, which is Monte Carlo Tree Search. And we will see how AlphaZero learns, what's this algorithm, how is it learning. And we will discover a specific algorithm, which is MuZero, which is an improvement over AlphaZero for complex environments. Like AlphaZero, it operates on simple discrete environments like chess or Go, but we need the domain needed to extend to more complicated domains. So these are the algorithms that did that, which is scaling to complex environments. And finally, we will see what's next. What can we cover next? Which is basically the Dreamer series, the Dreamer algorithms. That we will not see today because of time constraints, and it will take lots of time. But if you are interested, we can have another session about it. Let me check the chat. Okay. Bismillah. Background. Reinforcement learning. If I ask a question, how did we learn to ride a bike when we were kids? It's basic. The answer is so obvious. We have learned to ride bikes by falling off from it. We not just this, but for most skills, most human skills, we learn them by making mistakes. We never, for instance, got a correct answer in a in an exercise before if you didn't make an error. For instance, one joke that I always tell is that we never make recipes perfect at the first time when we cook. No, we need to make errors in a trial and error format in order to learn. And that's basically how humans learn, from trial and error. We learn from our mistakes and iteratively until we learn that specific skill. So the question is, why not apply such principle to machines? How or what a machine could do if it learns by making errors by itself. This question or this idea actually was proposed by Alan Turing yeah, in 1948. I think many of you know the Alan Turing, one of the pioneers of AI, and also the British engineer that has solved the Enigma, which was a complicated um, algorithm made by the Nazis. So he's one of the smartest computer scientists ever. And he thought of the idea that me and you have thought about today, which is implementing a trial and error learning in computer. Such idea appeared in the 1948 report made by Alan Turing, where he described basically a pleasure and pain system for computers. You can check this section later. However, I got this from Intro to Reinforcement Learning by Sutton in page 16. Intro to Reinforcement Learning by Sutton is one of like the most interesting and for most detailed books about AI. And if anyone is more interested to discover or read about such field, I will highly like the advise you to check this book. So reinforcement learning is the paradigm of machine learning or AI in general that is defined by learning through interaction, through trial and error, and through reward maximization, not like classification or structure discovery like supervised and unsupervised. What do I mean by interaction? Just like humans do, by trial. What do I mean by reward maximization? By making errors. So we need to minimize errors, and that's basically what I mean by this. Uh, Richard Sutton defines RL as the following. It's learning what to do, how to map situations to actions, so as to maximize a numerical reward signal. The learner or the machine is not told which actions to take, so it's not supervised learning, but instead it must discover which actions yield the most reward by trying them. Meaning we try or machine try many actions and multiple configurations until reaching the optimal decision making. That maximizes the reward. Formally speaking, a reinforcement learning problem is defined as a markup decision process represented by a tuple where where we have this agent environment interaction loop. So we have the agent, which is the machine. The agent, what it does basically, it operates in an environment or in a specific problem. It has the ability to take an action on the environment. It will receive eventually a reward and the next state of it, and so on and so forth. This is basically the agent environment loop. So this whole process or this whole formulation of reinforcement learning is uh, summarized by this section. We have a set of possible states for a specific agent, for a specific machine, and we will call it from now on an agent. An agent has a set of available actions, and we have basically two distributions that are very important. The first one is the transition distribution or transition probability, which tells what's the probability of receiving a specific of having a specific state given a previous state, and we took an action in that state. And the reward, which is the signal that the agent receives from the environment, and it's basically it's received after taking each action in a specific state. And the discount factor, we will talk about it in a bit. It would be good if we go directly through a simple example adapted from Sutton book to understand more this formulation. Let's say, for instance, our agent is a robot that collects scans, and it has a battery management system. So the aim is to build an agent that would basically smartly manage its battery while collecting counts. How can this be formulated by a markup decision process? It's by the following. So the agent, in terms of battery, so a robot can be in two different states, in a high battery state or in a low battery state, and it can take three main actions: search for cons, wait, do nothing, or recharge when it is in a low battery. If I wish if this, I think I've explained this well. If you have any questions, feel free to open the mic or in the chat. Yes, thank you. Then it starts searching for a specific kind. We give it a reward, a positive feedback that says to the agent that you are doing well. A negative way would be the following. If the agent is, let's say, in a low state, in a low battery state, it should recharge. So we give it a neutral reward, which is zero, and so on. If, for instance, the agent is in a low battery, and it starts and it keeps searching, we give it a negative reward as a feedback that the agent this robot should not search because it is in a low battery. It should instead recharge. So that's a markup decision process example. And basically, most reinforcement learning problems are formulated in this way. We start by defining what's the state space for the agent, what's its action space, what could the agent do, and we define the goal of the RL agent in general, which is defined by the reward. For instance, if we take another example for self-driving cars, the state of the agent can be what it is currently. So the image of what's outside the car, and the actions can be acceleration, deceleration, velocity, and so on. And the goal for the self-driving car is to reach the destination without making accidents, and we define the reward with respect to the goal. And this is basically the reward hypothesis. Okay, we will check it in a bit. Let's go back here. The properties of reinforcement learning basically are two. The first one, as I explained, is try and error. The second one is a delayed error, which is a very important concept, which says the following. The agent, if it takes a specific action at specific instant t, the impact of taking that action will appear not instantly, but it could have impact in the future. So what Sutton says in his book is the following: in the most interesting and challenging cases, actions might affect not only the immediate rewards, but also the next situation, and through that, all subsequent rewards. That's a very important property in reinforcement learning, and that's why here I explained which weights the future rewards. Okay, all right. What are the components of reinforcement learning? The first one is the policy. The policy basically maps the input or the state of the agent to the action. And the aim is basically to learn the optimal policy that would yield the highest reward, the highest sum of future rewards. And the policy can be deterministic. So we map a state to an action directly, or it can be a probability distribution. like this, where it maps a specific state to a probability distribution. For instance, in continuous case, we would map it to a Gaussian distribution, and so on. That's the first component of array. The second component is the reward signal, which defines the immediate goal of the agent. And the final aim of our agent is an optimization process. Its aim is to maximize the long term of these rewards, GT, which is the return. And here is the discount factor that I have talked about. Why we use the discount factor in array? Many reasons, but the most important one is that we give the highest rate to the immediate reward received after taking one action. However, we weight the future rewards with a specific gamma to the power of k, because if, for instance, gamma is actually between 0 and 1, and one can think about why we use gamma to the power of k is the following. If we sum an infinite number of rewards, and through no discounting like this, the series can diverge, which is a problem. That's why we use this factor, and different reasons. But the idea to keep here is the following: the aim of the agent is to learn the policy that would maximize the highest cumulative sum of rewards, which is discount by a factor gamma, which is a constant. The third component of any RL algorithm is the value function, and basically it says how is it good to be at a specific state. For instance, for the robot, if it is in a high battery level, it is in a good state. If it is in a low battery level, it's in a bad state. We define or we measure or how good state is with this function. And it's simple. It's just the mean of the expected reward starting from that state. Same thing for action value functions. It measures how good is it to take a specific action when being in a specific state. And it's the mean. It's just the mean of the expected sum of rewards, given that we start from that state and we take a specific action. Like here, for instance, we could do such process of calculating the expected cumulative rewards when being in a specific state or when being in a state and taking an action. And yeah, if we think about these intuitively, because this is important, let's say we are in a high battery state. For us, the best action to take is to search for cons. It's not good to wait when you are in high battery state, because you are just wasting your battery for nothing. And in the same time, it's not good to recharge because it's useless, because you are actually in a high battery level. So if we look at this combination, when we are in a high battery level and we start searching, we can say that the value function of this combination is high, because it's the best thing to do. And that's basically what these value functions are doing. They are just a numerical representation to measure how good is it to be at specific state or to be at specific state and taking an action. And finally, the reward hypothesis that defines the problem of reinforcement learning in general as an optimization process. The agent aims to maximize the expected return simply, which is the mean of cumulative sum of the discounted returns. Alright. We have defined the problem of array in general. We understood that the aim in the end is to learn the policy that maximizes the cumulative sum of rewards. Now we need to check an important intuitive way of how array algorithms learn. which is a very important concept, which is policy iteration. Policy iteration is one of the most fundamental methods for computing or for calculating an optimal policy, or solving the error problem in general. It alternates between two processes: policy evaluation and policy improvement. We will understand this intuitively in the end, but now let's just focus on these concepts, because in the end it will be very intuitive for you. The first step in policy iteration is the policy evaluation. Given a specific policy P, which maps state to actions, the goal of policy evaluation is to estimate its value function, because the value function, or even the action value function, they depend on the policy. They depend on the way we take actions, because the value function is defined with respect to the future rewards, which actually depend on how well we take an action or no. So policy evaluation in the end, its aim is to evaluate the policy. Starts to evaluate the policy from its value function. And what a way to do it? To do Bellman expectation. The value function is reward for plus of the next level state of the current state, which is low level battery, depend on its two future states. And this Bellman expectation equation, it connects this current state value with the value of the next state, which is very intuitive. And finally, policy improvement. The second process, whenever we know the value function, the agent can construct a new policy from that value function. Such policy selects the actions that maximize the expected value of the next state. In other words, let's say we have a value function. Let's say we know at a given moment the value of all the next states possible. The best way to approach the problem is to go or to reach the next state with the highest value, with the highest expected return. And that's basically what it means to act greedy with respect to a specific value function. That's policy improvement. It's just a way, it's just a way of getting a specific policy from a specific value functions. And policy iteration is just alternating between the two processes. This is a schema that represents intuitively what's happening, what this algorithm basically does. But let's say at a given moment, we start with a random policy that picks actions randomly, and we have a random value function too. What we should start doing, we first evaluate the policy, meaning we extract its value function. How would we evaluate each state given that we are following such policy? And from such value function, we act greedy on those states, on those values. And whenever we reach a new policy, we evaluate it to reach a new value function, and so on and so forth until we reach the policy that acts greedy with its value function, meaning that we have arrived to the policy, to the decision-making process that would always pick or get us from a specific state to the next state with the highest value. meaning that we have solved the problem. We have maximized the return, the return. We have maximized the expected sum of future rewards because we are in the policy that is acting greedy with its value function. Policy iteration is basically the basic or the most basic idea, the most important idea in most of reinforcement learning, in the most RL algorithms, like we will see in a bit. And I wish that this was a little bit intuitive for you. If you haven't understand, you can type in the chat. Yeah, okay. Can we approximate the value function, like using neural networks to do this? Yes, Amy, for sure. Um, the first type of or the most basic way to approximate value functions is using tabular, like a tabular format. You map each state to its value and you update it in a tabular format. This is when you have very limited number of states. However, when the state space or the specific state is a tensor, is an image, we cannot store each image with with each value. So what we do, we approximate the values with neural networks. And yes, neural networks are generally known as general function approximators. And yeah, they are used to do so. Okay. Moving on to the next concept, value-based methods. These methods, they are a type of RL algorithms, and they aim to learn how good each state or state action pair without explicitly representing the policy. So here we have seen policy iteration concept. Value-based algorithms, they basically do not, they, the policy improvement step is done in the end. What we are doing in value-based algorithms, basically, we are trying to improve the value function each time to act greedy until reaching the optimal value function, and we extract the policy by making it greedy with respect to the value. Um, in other words, value-based methods are general reinforcement learning algorithm methods that estimate a value function that guides the action decision making. One of the most famous algorithms is Q-learning. I think those who have learned before about RL know it. I will try to explain it quickly and intuitively here. And my slides say the following. In model three, let's forget this word. In value-based reinforcement learning, agent updates value estimates directly from experience by interacting with the environment. Like I said before, by trial and error. We use bootstrapping methods like TD learning, temporal difference learning. All right. Let's say the agent is interacting with the environment. It has a state. It tries a new action and it needs to update its representation, its knowledge about how good is each action or state action. Like I said before, in value-based, what we are doing, we are learning a value function. And to learn a value function, we basically do updates on our knowledge about these. And this update is known as the TDR update. At each time step T, when we try a new combination and we receive a new reward, we update our already uh, already assumed value function in a mean in a running average mean or in a running mean. Yeah. Let's say the value function of taking a specific action at a given state is already initialized at 0, and we took a new action which is 80. We received the new reward, and we need to update our value function. What we do, we we have the last or our known or our old value, which is let's say what was initialized to zero, and we have a new estimate that comes from the environment, which is the new received reward from the environment, plus the discount factor multiplied by the maximum of the next of the action of the next state maximized, meaning that we are in a specific state. We took an action. We will receive a new reward, and we will take a new action. The new estimate given us by from the environment is the sum of the new reward plus the value of the next state with the next action. However, here we assume that we are acting greedy. We are following a greedy policy. That's why we take the maximum. We take the action that maximizes the value function of the action value function. And that's basically the update. In other terms, this is the new estimate. When alpha equals 1, alpha is the learning rate. When it equals 1, we discard the last value. We take only in consideration the new estimate given us from the environment. When alpha is 0, we do no update. When alpha between 0 and 1, we are updating our old estimate with a running average in this way. And basically, for tabular algorithms, this update or this algorithm, it's an iterative process. While for instance, while true, take new action, update the value function, and so on. And by the estimate, our value function converges. We extract the optimal policy by making it greedy with respect to the value function with the following equation. For sure, for each state, we would we would want to take the action that maximizes the value its value function. Meaning we take the action that has the highest return. All right. That was about 20 or 25 minutes recap about reinforcement learning in general. I wish I was a little bit clear. If anything was not clear, please you can ask me here before moving to the next step. Ah, is discount factor bounded value? What is expected if it is set to its power bound? Yes, the discount factor is bounded. It's also between 0 and 1. Um, Let me go back to the slide. Okay. If gamma equals 0, we basically see only the immediate reward. We don't see the following rewards. Let me go back here, but it will be better. Here we have the return. It's the expected sum of future rewards. If gamma equals, meaning that we don't see the next rewards. If gamma equals 1, we basically weight all the future rewards with the same weight, which is 1. If gamma between 0 and 1, that's basically generally the case. I would explain better with Excalibur. Okay. We are in a current, let's say, for instance, we are in a state, we execute an action, we receive a new state. Okay. st at instance t. We are in state st. We pick an action st corresponding to the output of our policy. We will receive uh, a new reward rt plus 1 and so on and so forth. We will receive by the end plus 3 plus 2 plus 1. Um, the return, which is the cumulative sum of future rewards, is calculated as the following: t plus 1 plus, let's say, g, which is gamma, multiplied by t plus 2. Um, gamma au carré fois rt plus 3, and so on. That's basically the equation of the return, which is the quantity to maximize. If g is set to if g is set to 0, the return will be just the immediate reward, so we will not see the future rewards. If g is set to 1, gt will simply be just the sum of all the rewards, and so on and so forth. If g is between 0 and 1, it would be a normal gamma multiplied by this plus gamma square. And when we reach, or by step 30 or 35, gamma to the power, like a small value, for instance 0.5 to the power of 40 or 50, it would converge to 0, the gamma to the square. So basically, even like with the return, whenever gamma is between 0 and 1, it at certain future step, we will not take the subsequent steps. So yeah, that's my answer. Omar. When can we have? I wish this answered your question, Omar. When can we have alpha 0 and 1? Like its learning rate. Can we take it 0? Yes. Let me go back here. Um, in value-based methods, when we set the learning rate equals 0, it basically means we are not learning. We ain't learning nothing. We just keep affecting the quality, or the action value function receives the odd action value function. We are not updating. If we set alpha equals 1, we are always discarding our last estimate of the action value function. We always take this. Uh, this is affected to this quantity because alpha equals 1. This will cancel with this. And the optimal case is to set alpha to 0.01 or a very small value, because this is a running average. And when we iterate multiple times, this will eventually converge to the to the to the value function of the optimal policy. And this is basically what is done in practice. They set alpha very small, and they set gamma to be 0.99 or 0.999. Okay. I wish this answered your question, Amir. Amir, let's advance more to model-based reinforcement learning and planning. Um, a model-based reinforcement learning. The first question that comes to us is, what is a model? A model for an agent is anything that would allow the agent to predict how the environment will respond to its actions. And generally, models are stochastic. There are several possible next state and next reward, each with some probability of occurring. If we go back here in our case, or in the general case, in the general case, the agents in reinforcement learning problems, if they take a specific action, they don't know what to expect. They don't know the next step, and they don't know the reward. In model-free problems, we don't have a way in model-free reinforcement learning methods. We don't have a way to predict what's the next step or what's the next reward until we execute the action on the environment. But in model-based reinforcement learning, no. We have that model. We have a way to predict if we are in this state and we take this action, we will know specifically what's the next state to receive and what's the reward. Model-based reinforcement learning employs such idea, and the model it can be given, provided in very simple games, or it can be learnable. And this is basically the advanced concepts of model-based reinforcement learning. It's when we don't know the model and we want to learn it. The second question, which is very central in model-based reinforcement learning, is what is planning? Planning is generally, in such class of methods, is a computational process that takes the model as the input and improves the current policy for interacting with the model environment. Intuitively speaking, let's say I always love to take like to take this example. Let's say you are playing a chess, or you are playing a strategic game like chess against another person. Before taking a specific action, before taking a specific piece here or there, basically you do planning in your head. You do planning in your model of the world, like in your mind, which is the model in our case. You plan. You say the following. Um, if I take this piece to this board place, what would happen? How would the other person react? If I take this piece in another place, what would happen? So basically here you are doing planning. You plan the next action to take, but before you think, you go through a process. And the model, in your case, is your thoughts, your mind, how the person react, what he could do, and so on. And after your thought, after doing planning inside your brain, you take the action, or basically you improve your policy, you improve your decision making. Model-based reinforcement learning is exactly use this concept of planning using a model. The model can in the case of us humans, it's our brain, it's our thoughts. In the case of reinforcement learning, generally uh, it's the function that would tell the agent what's the next reward, what's the next state if you receive a specific if you take a specific action. What's planning? We will see it. Planning in your head was testing multiple configurations until reaching the most optimal for you the most optimal action. In the case of model-based reinforcement learning, it uses specific concepts used called Monte Carlo Tree Search. So in the end, if I resume model-based reinforcement learning in few words, it is learning a model or using an existing model of the world to plan to get an improved policy. And that's how it's basically defined in Sutton book. Okay. Dino, one of the first algorithms, model-based reinforcement learning algorithms, it was maybe in 1980s or 1990s. It uses planning, learning, and action in the same time. And its idea is very intuitive. It's just like pure learning, or that it uses the TD update that we have seen. Let's go through it step by step. We initialize the value function values, the value to learn, and we initialize the model that maps states and actions to the next reward and the next state. So we have gone through a process of initialization. What we will do basically, the first five steps, they are very well. The first four steps, they are like pure learning, the algorithm, the value-based algorithm that I have spoken about. We will loop forever. We will loop until convergence. We are at the current state. We act greedy with respect to the value function. We take the action that has the highest value function. We observe the next reward and the next state, and we update. We update our estimate based on the TD error. These are the model free value based algorithm. What Dyna have integrated in addition to this is a learnable model. What this basically does, simply speaking, this model just saves the reward in the next state. So basically, what we are doing, what's the model in our case? It is just saving the output of our previous actions. So in the planning phase, what we do basically, we update our estimates based on our already existing entries in the model, or based on actions and states already seen, already saved in our model. What we do in the planning step, we select a random action existing in our model seen before. We select a random action taken in a specific state. We have the model that returns the reward and the next state. This returns these because they were already seen and they were saved here, and we do the update. So this was the model free part, the simple one, and this was the planning part of DynaQ. In Satin book, uh, okay, I will go back here in a bit. In Satin book, he had a specific implementation of a specific environment. This grid environment basically represents a reinforcement learning problem. We have an agent starting at this place of the grid, S, and its aim is to reach the G, the destination. And the actions of the agent are go left, go right, go up, go down. The aim of the agent is to reach the destination in the least minimum number of steps, with the minimum steps. So the reward goes as the following. At each step, we give it -1. Why? Because we want to reach the destination in the fastest way possible. Um, so in the book of Sutton, they tested three implementations. The, the first implementation used zero planning steps, meaning we have omitted this second part. We didn't do planning. We didn't have a model. The second algorithm was tested with 5 planning steps. The third one was tested with 50 planning steps. And this graph basically compares the three algorithms in terms of how fast each algorithm has learned. We have here the access to episodes, how many episodes the algorithm has taken in order to converge, and here the number of steps per episode. For sure, the less is the number of steps, the better the algorithm. For instance, let's focus on this graph. Zero planning steps, direct reinforcement learning only, no planning, no model. The algorithm has taken about 30 episodes in order to reach the least number of steps to reach the destination, which is 14. And if we do it together, it's simple. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, 13, 14. This is the optimal path, 14 steps. So the first algorithm with no planning took more time, took about 30 episodes. The second algorithm with 5 planning steps, which is here, loop for n planning step. It has taken um about 3 episodes or so. For 50 planning steps, it was so fast. It took about 2 or 3 episodes. So this demonstrates in very simple maze environments that actually planning is effective. It's effective to have more planning steps is better than have small planning steps is better than uh, having no planning mindset planning steps. Okay. Um, DynaQ is it was a very simple algorithm that gives us an idea about how can models be learned or how can we integrate models in trial and error algorithms. And I know if we take its schema, if we observe it a little bit, what we have the direct reinforcement learning update, which is this one, um, the Q learning update. Basically, in order to do such updates, we need to interact with the environment. So, through real experiences. When we interact with the environment, we have new states, new actions. We do direct reinforcement learning updates to improve our current value function estimate or our policy. But in the same time, from such real experiences, we learn our model. We save the last entries, the last state and actions encountered, and for this model, what would we do with this learnable model? It's to do search control through simulated experiences or through planning steps. The planning in our case is the previous 16 actions and states. Okay. So if we summarize since so far, we have understood what's a model. It's anything like functions that would say the agent the future, that predict the next. That's a model. What's a planning? Planning uses such model in order to improve the policy. And Dino is one of the earliest model-based algorithms used in such um, in such class of methods, which is model-based. Before going a little bit further to Monte Carlo Tree Search, do anyone have a question? Yes, it's getting recorded. Um, okay. 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 Look ahead, sir. Monte Carlo Tree Search. What's Monte Carlo Tree Search? What is MCTS and what is its relationship to model-based array? Motivation. First of all, before going a little bit further, Monte Carlo Tree Search is a very general concept in computer science. It's actually a heuristic. It's one of the heuristics methods used of like in classical methods, and it was integrated in model-based reinforcement learning for a specific reason that we will discover together. All right, Monte Carlo Tree Search is a method that helps us make better decisions by simulating the future, rather than relying on only on learned value functions or policies. For example, in games like Go or chess, we computing a full value function is hard because you have many states, you have many actions. It's like actions grow in an exponential way with respect to the state and with respect to how far we have advanced in that game. But we can simulate from the current state many possible futures using a model or using a tree format. So Monte Carlo Tree Search would allow us to, instead of learning global Q values for all the combinations of states and actions, we focus computation on the current decisions. And we use the tree structure, which is in Monte Carlo Tree Search. I will advance a little bit in the slides to explain this concept more. And alright, this is actions to take. Let's say we are playing the X. We have the letter X. We can put the letter X here, or here, or we can put it here. Three combinations. Monte Carlo Tree Search would what would it do basically? It would simulate if we take X here, how would the environment respond? What's the new state? This is the new one. If we put X here, what's the new state? And that's the new state, and so on. And here, we are in this current state. We are playing with O, with the letter O now. We can put the letter O here or here, and so on and so forth. That's Monte Carlo Tree Search. It's basically from the current state, we simulate multiple paths, multiple actions, and we see how the environment would react. This is similar to playing chess or playing strategic games. In our mind, we simulate such stuff. If we put the piece here, how the environment would react, and our opponent, which is this one here, how would he react? Would what could he possibly take as options, and so on and so forth. Monte Carlo research, as a summary or as an intuitive process, or as a simulation process, like as an analogy to how humans think and learn, that's what MCTS is. MCTS doing planning in multi in a tree format, then by the whether based here or learnable function. Okay, so yes, the setup of Monte Carlo research in the classical one is we have a deterministic or stochastic model of the environment, like this one. The model of the environment for us here is known. We know if we put X here, we know where it would place itself if we put X here and here. So we have already a model of the environment in our head. We know how would the environment react. The second component of Monte Carlo research, Monte Carlo MCTS, is the policy, a roll-out policy to simulate actions beyond the tree. The policy is our current way of thinking. If we think to place the X here, that's the policy. That's our way of thinking or the decision making. The third component is a tree that stores two important values: the action value and the number of visit counts. Going back to this example, I think I have another one. That's a very big answer. Yes. Let's go back here. How to is the model of the word, the model, the simulation the simulation, which can be learnable or known. Like for us, for X and O game, it is known. And finally, we store for each node in our tree, we store two important values. For this add, we would store its value function. We store in this add what's the value of taking the action of putting the letter X here when we started with this one. So here we are storing the QSA, and we store the visit counts. So for each edge to take this state, or we visited this path. Why? Because in Monte Carlo Tree Search we will build the tree iteratively. We will then afterwards try this action, reach this one. Then we go back to the next one, reach this one. Then we go back to the next one, reach this one. And we go back to the to the root. We try new action in this tree. We intuitively, in the end, we will take the path or we will take the edge that would yield the highest value function. That's basically how Monte Carlo research behave, and that's very similar again to how humans learn chess. Um, okay, we have no questions so far. Um, Monte Carlo tree search to build the tree. Basically, it's algorithm. We have four steps. Uh, we have the selection, expansion, simulation, backup, and we repeat. We repeat as many times as we want. It's a loop. It's an iterative process with a specific number of steps specified by us. Let's say, for instance, here, this is our current Monte Carlo tree. This is the initial state. We can, from this initial state, take three actions. We have taken three actions, right? And we keep digging. Uh, uh, we keep going through this tree. The first thing is to select which one of these three paths remember, these steps are to build how to build the Monte Carlo research. The first one is to go through this tree and select the path, the current path to take. The second step is to expand. Whenever we reach, for instance, here or here, we have, for instance, selected to take to take this action, we reach this state, and we take this action again, we reach a new state. And here we have two possible options. We want to take an option, but it is unexplored. It is unexplored because it does not have a state connected to it. So what we do basically, we expand. Expansion meaning trying exploring new option or expanding a node means we would add its whether add new options or add a node, and yeah, that's expansion. The third step is simulation. Whenever we add a new node in our research, meaning we have added a new state in our tree, we follow a specific policy, rollout policy or a random policy, and we keep we keep building, we keep trying taking actions until the episode ends or until we have finished the game. We have finished the chess game or finished the XO. So that's the simulation process. When we finish the game for sure, we will have the output. We won or we lost. And for this in this specific case, we will have a value, a new a reward that tells us if we won or if we lost. We use such value to back up, to update our estimates, to update each edge, to update the visit counts, and to update the value function with respect to the outcome of that game. Okay, I would like to repeat. This is how Monte Carlo Tree Search is built into 4 steps, and the following slides detail a little bit into how is it built specifically. The first one is the selection. We traverse the tree from starting from this root using a tree policy or using our current policy, and we select an option at each node that maximizes this specific quantity. Let's say we are in a specific state and we have multiple actions to take, and we want to explore new actions in the same time. So we would want to take the action that, according to the tree currently, maximizes the value function, which is this one, this estimate that is getting updated iteratively. This is a little bit greedy. We are taking an option that maximizes our current estimates based on the tree. These are new actions that were not taken into account divided by the number of visit states and actions. Let's forget about the alien and the square. Let's just focus on the intuition. If the visit state of this or with the huge, it be very the tree. We maximize this the outcome of that game, we back up. We back up the visited path. So for each visited path, we would increment its visit count and we would update our value function in a running average way. This is incremental average update of the Q value. Let's say, for instance, G in our case was the sum of rewards in that path. In the end, we will have the whole return, and with that return, the outcome of that game, we update our estimates of the value functions with this one in average. Uh, okay, this is the new estimate. This is the old estimate, and we are updating the value in a running average way, and we call it a backup. And that's how basically Monte Carlo Tree Search is. The aim of this is that after specific number of simulations, we will have a better action. We would have a better decision making, a better policy to follow. So from the root, we select the action that better maximizes the value function or the action with the highest visit counts. So in the end, Monte Carlo tree search is similar to how humans plan in their mind. We try multiple scenarios in that strategic game. We assume many hypothetical scenarios. Then we take the most promising path, the most promising action. That's Monte Carlo research. What it does basically in the end, it takes the most promising greedy path, like this one, because we were updating the value functions each time when we were building the tree, or we take the action with the highest number of visits. Okay, this is a summary of how MCTS behave or how is it built. And this is huge Monte Carlo tree search for X and O game. This is new state, new state, new state, and so on and so forth. This was generated with graph if you know it. And this is a simple like pseudo algorithm that you can check. We can check together. We loop through a specific number of simulations. The first thing is we select the node when we are traversing the tree. Action equal tree policy. We select the action that maximizes that quantity. That we call it UCB. Sorry, this quantity UCB, upper confidence bound, and we append the node, the new state, and the action, and so on and so forth. Then, whenever the node, a specific node, is not fully expanded, we didn't test its actions. We try a specific untried action. We expand it. We add it to the tree, and finally, we do the simulation step, and we back up. We update our old estimates in order to return the best action. That's Monte Carlo research in in short time. بصح إذا نلخص وش قلت كامل ولا وش هي الفايدة من Monte Carlo research in the end regardless of how it is built, it's simply starting from a specific state we try multiple actions, multiple configurations, and we try multiple game scenarios. We back up our estimates of the value function, and in the end, we take the next action with the most promising value or the highest number of visit counts. And AlphaZero, I believe many of you have heard before about such algorithm. It uses Monte Carlo research in a very brilliant way. But before going further into AlphaZero or AlphaGo, does anyone have a question about MCTS? Tree of thought, exactly, yes. Large language models, large reasoning models employ such concepts. They employ concepts from model-based reinforcement learning in reasoning models. Yes, chain of thought and tree of thought. Mhm. Um, since no question is asked, I think I move forward. If you want me to revise any specific concept, please tell me. Like we still have time. Uh, else I will advance. So what do you think, guys? Do you want me to advance or do you want me to go back to a specific concept? Okay. Um, Ayman, you can open the mic. Anyone can, like, you feel free to open the mic at any moment. Okay, I will do so. Um, AlphaGo, AlphaZero, beating world champions in chess. I think many people have heard about AlphaGo or AlphaZero, and many people, the humanity, witnessed an AI system that beat a human, the world champion in Go. Go, which is a very complicated game with many, many combinations. In a specific state, there are many exponential actions to take. And beating a human world champion in such very strategic and complicated game is an achievement that, and it was a huge breakthrough back in 2017 or 2016. There is also Dota, but I believe it didn't use model-based AI. However, what's AlphaZero? It's a model-based reinforcement learning algorithm for sure, but it learns to play games like chess, Go, Shogi, which is a board game, by self-play, by playing by itself, and by combining neural network deep learning with Monte Carlo Tree Search. What do I mean by self-play? In our case, self-play is a process where the neural network or the agent plays against itself and try to improve itself from that from that self-playing. How would I explain it? Um, let's say the computer in the beginning does not it a specific machine does not know how to play chess. It only knows its rules. It only knows the rules of chess with the different combinations, and it knows that each game its output -1 if it loses, 0 if it's a draw, +1 if it's a win. In self-play, in this process of self-play, the computer try to play against itself iteratively. How, like in using Monte Carlo Tree Search, how is it possible that someone plays against itself? If we go back in here, in Monte Carlo Tree Search of XO game, in this first level of our Monte Carlo Tree Search, we had the letter X. In the second level, we have the letter O. So Monte Carlo Research supports like two-player configuration. The first in here, it's the machine that took the action. In the second level, it's the adversary, the other one, the opponent that took the action, and so on and so forth. All right, that's self-play basically in AlphaZero. And AlphaZero combines a neural network deep learning model. We will see what does it predict exactly, and we will see how it uses Monte Carlo research. But like as a schema of what AlphaZero is doing under the head is the following. It's the first piece of the algorithm is self-play. We use self-play process to generate data, to generate many, many trajectories, and we use Monte Carlo research given a specific state to give us a better action at each state. We have understood why Monte Carlo yield a better action. With this self-play data, we improve the current policy by adapting or updating our neural network with respect to a specific loss that we will see. And the process is iterative. We self-play, we do play many games. The computer play against itself many times. It uses Monte Carlo to generate better better options. It improves its current policy, its current neural network, and we do the process iteratively. So here this is self-play, here train and evolve. What's the setup of AlphaZero? We know two things. The outcomes of this game, like I said, they are three. -1 if the computer loses, +1 if it wins, 0 if it's a draw. And the network, the neural network in the case of AlphaZero, outputs two values. The policy vector, the prior probabilities of the move, the policy vector outputs the probability distribution given a state. So this is obvious, we know it, and it outputs the value estimate of the neural network with respect to the state. And Monte Carlo Tree Search would use these priors, this old policy. The Monte Carlo Tree Search would use this policy and this value estimate to guide the search and the build to build the tree. And self-play games would produce targets, would produce better options used to train the neural network, and the process repeats iteratively. Starting with Monte Carlo Tree Search, um, it's similar to what we have seen here. It's a very similar process. Simulation. We call the neural network to give us the value. So we do not continue executing the game until it ends. No. Whenever we reach a new node, we call the neural net value to the earlier states. That's the only difference and between Monte Carlo Tree Search for AlphaZero and this heuristic algorithm. So it's a bit similar, but it's simpler because since we have the neural network that predicts the value estimate, no need to continue executing the M until the end. We would use this estimate in the Monte Carlo Tree Search when building it. All right. What's the input for Monte Carlo Tree Search? It's similar to what we have seen. The input is the state, the current configuration, for instance, for the test game, and the policy network. That would output the policy and the value network that would be used in the backup step. Monte Carlo Tree Search. Its advantage, or why Monte Carlo Tree Search can output a better action? It's for four reasons. The exploration, like we said in the selection phase, we are exploring new combinations of actions that were not explored. It uses look-ahead search because it tries multiple actions at a specific depth. It uses averaging of few values, like we have seen in the backup step, and it runs for many simulations. So why would it yield a better option from a specific state when we take? Why would it do this? It's because we have a specific way of thinking, but we expand it. We try multiple configurations at multiple levels, and we update our estimates of we learn or we until this process yields an improved policy. So I can say that Monte Carlo research is a policy improvement operator. So the output of Monte Carlo research in the end, given a state and the current policy network, is a better action or a better probability distribution. And it's actually the target that would be used to update the policy network. Self-play uses Monte Carlo research For MCTS, it's called only for only one state. Uh, okay, it's only used for one state, but self-play is used to generate specific game. It calls Monte Carlo Tree Search to collect the game trajectory. So starting from an initial state, we call the Monte Carlo. We have a new target, which is the policy. We execute it in the environment, and we receive a new state. We use Monte Carlo Tree Search to, and so on and so forth. All right. So self-play, its input is the policy network. Its output is the set of states encountered during the game, the policy search for each state, the improved policy for each state, and the outcome of that game, which is -1, 0, or +1. This is for one game. So what's the laws in the case of AlphaZero? Let's remind ourselves that AlphaZero basically predicts two quantities: the value function and the policy. So the loss for one is the following: the difference between the outcome of that game and to be close to the outcome of the different games. So we minimize mean squared error between these, and we want our current policy, to be close to the search policy, or to be close to the policy that was improved by Monte Carlo research. So we minimize the cross entropy law. This is the cross entropy. We make the probability predicted by network closer to the search policy. So that's the loss, the first value. And the second term, train with stochastic randomized optimized mathematical function. We and a trial with the old model before the training, and the new model wins against the old model. It means that we have learned better policy. So self-play games. إيش معناتها هنايا؟ معناها the computer in self-play games تعلم شغل new actions from Monte Carlo research. من بعد يلعب شغل راح يلعب counter the old program or the old model. إذا تعلمنا new actions معناها ربحنا معناها the new model wins. We update the parameters of the current model as we keep it, and we try and we play for other games, and so on and so forth. That's basically self-play in AlphaZero. Um, that's AlphaZero algorithm. I guess I have summarized it as much as I can. And actually, AlphaZero is a generalization over AlphaGo. AlphaGo was made initially only to play Go game. Then AlphaZero generalized AlphaGo for more games like chess. And one of the most interesting applications of AlphaZero tensor is AlphaGo tensor is Alpha Tensor. Alpha Tensor is an model-based reinforcement learning algorithm that uses AlphaZero to discover algorithms. AlphaTensor, its application was actually to discover a better matrix multiplication algorithm. It uses AlphaZero under the hood. It considers matrix multiplication as games. It uses self-play games to try out multiple configurations of or multiple transformation of the code or the algorithm. And the aim is to learn to minimize the number of operations to 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 take. So Alpha Tensor is one of the most amazing applications of AlphaGo, and it has its repository, it's public, and if like we can have also another video session to talk about Alpha Tensor and how it uses AlphaGo to discover new matrix multiplication algorithm. Why this is actually important and fascinating at the same time? We know that deep learning models, they transformers, LLMs, VLMs, they all are bunch of matrix multiplications on GPUs. And matrix multiplication, it consumes time. It consumes time and energy. If we discover a new matrix multiplication algorithm that is enhanced and consumes less instructions in less time, this is a huge, like a huge leap in or a huge discovery in the field of AI. And Alpha Tensor was like AlphaGo was AlphaZero was used to do such breakthrough discovery. I also searched since that it has not yet been populated. It's not used in production. Maybe they are trying to scale it to more huge more matrix multiplication shapes. But yeah, this is an interesting application. And we have the second application of AlphaZero, which is AlphaGo, which is basically winning games. All right, we don't have much left. The most important part, we talked about the most important part, which is AlphaZero, Monte Carlo Tree Search. I will talk quickly about MuZero and Efficient Zero, how they compare to AlphaGo, and what they did add exactly. But before going on, I would mention that AlphaZero is AlphaZero is model-based algorithm in a way that it uses Monte Carlo Tree Search and it uses an assumed existing model. Uh, I said something interesting in the beginning, which was um, the AlphaZero agent for chess knows the rules. It knows if it takes, for instance, specific base to a uh, specific base to a specific uh, table position, it will know where it will fall exactly. It's deterministic environment. And the second rule of the game is the output is -1, 0, or 1. So it knows we have a model of the world. We have a model. We know the outcome of the states. We know the outcomes of actions, and we can predict the rewards. So that's why it's model based. It does not learn a model because the model already exists. That's it. Do you have, please, any questions regarding AlphaGo? Mm, Uh, guys, I have a question. يا كنت تشوف السلايدز تبعي.
Yes, can يبان كان يبان.
أيمن. Okay. Ayman, you can open the mic. If you have any question, please feel free to open the mic directly. Uh, before we advance to MuZero. No question. Ayman was typing. Ah, Ayman was typing.
No, no, no. I'm not typing. شغل راني في الشات برك.
Oh, okay. So if you don't have any question, I will uh, go to the last part of our video session. Oops, here. Mu zero, efficient zero. These are two algorithms. They were published in the first one, MuZero, in 2019, I believe, or 20. Well, AlphaGo, AlphaZero, they were published in 2016, 2017. MuZero and Efficient Zero in 2019, 2020, and they scaled the AlphaZero algorithm to more complex environments. I put here an emoji. It's an Atari game. Atari, for those who are a bit into reinforcement learning, Atari is one of the most famous benchmarks in reinforcement learning in general, and AlphaZero cannot operate in Atari games. Why? Because it assumes perfect knowledge of the rules of the game. It assumes it has already an existing model. It knows the outputs of the different options, and it can predict the outcome of the game, win, loss, or draw. MuZero, Efficient Zero, they scale such algorithm to more complex environments and to more complex problems where we don't know the role of the games and we don't have a perfect model of the world. So these algorithms, what they do basically, they learn a model. What's MuZero? Starting with MuZero, because Efficient Zero is just MuZero but enhanced for specific reasons. Uh, like AlphaZero, MuZero combines Monte Carlo Tree Search for look-ahead planning, we know it, and the neural network trained with self-play and bootstrapping. We know these. They are exactly like AlphaZero. But unlike AlphaZero, MuZero does not rely on the true game rules. It does not have them. It does not have access to them or transitions during search. Instead, it learns three internal functions. Uh, in Atari games, for instance, Atari game for those who know it, we have, for instance, Space Invaders. We have this Space Invader, and like you can move it left or right to like avoid getting shot. If it goes left or it goes right, it does not know exactly. It does not have a model of the world in the sense that maybe like how would I say? A shot can get in this direction when it goes here, but it will come without knowing it. So it cannot predict the output of like it cannot predict if I take this if I go left. Yes, it will know that it will go left, but it does not know how the environment would react, how where the bullets will come from. Okay, so Neo Zero, the main difference is it does not know the true game rules in the sense that it cannot predict the next state, the next action. If it takes state, it cannot predict, if it takes an action, it cannot predict the next state. So what it does, it learns the model. It learns the model of the world. How? It uses three internal functions. Let's start with the prediction function. It outputs a policy and value from latent state, just like Alpha Zero does. But in addition to this, MuZero is learning a model of the world. So it learns two new functions, representing first one is the dynamics function that represents the environment. It predicts the next state and immediate reward given a latent state and an action. And the representation function, it encodes the observed state into a hidden latent state. And MCTS runs purely inside the learned latent model. What do I mean by latent model? What do I mean by latent state? And what's the difference between an observation and latent state? Okay, let's see this um, illustration. Let's say we are playing XO game again, and this is the current table configuration. This representation, this grid representation, is an observation. It's an observation OT. It's an observation of the environment. And the age. And this is the Monte Carlo Tree Search. This is basically the step where we do planning. We do planning in a different space, state, or state representation different than the observation. We do it in a space called the latent space. The latent space, what is it exactly? It maps all the previous observations, all the previous scene configurations to a single vector, which is the state. So this state in our case is just a representation of all the previous configurations, outputted by a function, a neural network, H, called the representation function. What this does, it converts a sequence of observation into a hidden latent state. Uh, Unlike AlphaZero input, which is single board game, MuZero can handle partial observability. It does not this does not give an intuition, but I will give another direction for you to understand. I will say the following. The first thing first, in complex environments, we need to have some sort of memory, some sort of representation of the previous states, like uh, the first table configuration, the first observation O1, representing the first table configuration. We take an action after doing planning. We receive a new observation, new configuration, and so on and so forth. At the observation number 30, we need somehow to have an idea of what were the previous states. So we run these on an RNN or an LSTM, that to make MuZero or to make the agent uh, contextually aware or aware of the previous time steps. That's the representation function. That's why we go from the first observation up to the current time step. So the latent space is just uh, mapping all the previous presentation into observations into a compact one vector, one state vector. And afterwards, we run Monte Carlo Tree Search and our planning into such latent space. Why we call it latent? Lat- Latent variables in the general case, they are representations, but we don't know why the neural network did learn such representation. It's latent in the sense that it's not uh, a random variable that is explained by us. No, we cannot explain it. It's like learned under the hood. That's why we call it latent space and we call it latent state. So that's the aim of the first function, converting a sequence of observation into a compact hidden latent state that will be used inside the planning of Monte Carlo Tree Search. The dynamics function, we know it. It's just how the neural network is learning the model. It maps state and its corresponding action to the next reward and the next state. This is basically what mainly locked in AlphaZero. AlphaZero had access to this. It will know for the rewards that all the immediate intermediate rewards are zero, and it can't predict also the next state. It's just the new table configuration. In MuZero, we don't know. We don't know how, the next reward and the next state, so we learn it through a dynamics function. It predicts the next state and immediate reward from the current latent state and action, and it's used here in Monte Carlo Research. I will explain how it is used in a bit. And finally, the prediction function. We know it. It's just like AlphaZero. It outputs the policy and the value of the state. Okay? MuZero is just like AlphaZero. It uses Monte Carlo Tree Search to do planning, and it uses self-play to generate games, and the training loop is very similar. The difference is that in Monte Carlo Tree Search, what we do, we reason or we do planning in the latent space with those latent states. So the first thing to do is to convert the previous observations. Here in the Monte Carlo Tree Search, we do it in the latent space. So we convert the observation to a compact state. Then from that state, we make a call to our neural network to give us the probability and the value of this state. And then we take the action with respect to the policy network, our current policy network, and we start building our Monte Carlo Tree Search. But if you remember very well, that in each edge of the Monte Carlo Tree Search, we keep a running average Q of SA to say to say uh, to say how well is each path. But in order to estimate these, we need to have access to the reward from the environment. If you remember in the backup, uh, in the backup step, the Monte Carlo Tree Search, we estimate the G. The G is given by the environment or given by the model already known by AlphaZero. But the backup step in Monte Carlo Tree Search from MuZero, it uses those rewards, those learnable rewards. That's why in each step when we take an action, we make a call to the dynamics function. It will predict the next state and the next reward, and we keep simply building the tree, so on and so forth. That's Monte Carlo tree search planning in the latent space. Then after building the Monte Carlo tree search for a specific number of trials, we would in the end pick the most promising action, the most promising path in this latent space, with a specific metric, the action that were visited the most, or the action of the highest value, Q, Q value. So what's the difference? When we do Monte Carlo research in MuZero, we don't execute it in the environment. We execute it in an imaginary world, in a latent space, or like in a dream, in an imaginary world that does not correspond to the current environment. Here we do not interact with the environment. We plan and we use planning in our learnable model. I wish the idea was. It's a bit hard, I believe, to understand to get in the first step, but as an intuition to give you from me is the following. In planning, we do not want to interact with the environment. In planning, we are again trying multiple actions, but this time we do not execute it in the environment. We execute it in our learnable model. This here, this Monte Carlo research, it's executing the actions, predicting the values, and so on in an environment different than the actual one, but it's a compact representation of it. That's why we call it a latent space. And yeah, for B, we know this. It's very similar to AlphaZero. At each at each observation, we run a Monte Carlo tree search. This will yield us a better policy. It would give us an action. The action would give a new observation, and we run it, and so on and so forth. This is the self-play step, like AlphaZero. So the only difference was in using latent space in the planning. And yeah, and finally, the second difference بغير بغير latent space planning Monte Carlo research we have explained this if in self play it's the same thing We run Monte Carlo Tree Search for multiple steps. We get new action. We execute it in the environment in set play, observing next observation, and so on and so forth. Just like AlphaZero. The main difference, this main second difference with AlphaZero is in the training. In the training step, what we do, we need to update three functions. Well, two. The third one is updated like implicitly. We need to update how the model predicts the reward in the next state. We need to make the model also learn to predict a better policy and to predict a better value. That's why in the loss function we have mainly three parts. We have the first part is the value loss, just like AlphaZero. It's minimized mean squared error between the target return and the predicted one because our neural network predicts this. We have the second one, similar to AlphaZero, minimize the cross entropy between the target, the neural network, our neural network predicted policy, and the search policy output by Monte Carlo Tree Search. And finally, we need also to uh, learn correct rewards. That's why minimize in the loss uh, the mean squared error between the observed reward and the predicted ones in this step. That's the addition of MuZero to AlphaZero. It just had added the notion of planning in the latent imaginary dream world, and in the same time updated the loss function to match this. To learn the model, we need to learn correct rewards and we need to learn correct states. But the trick here is that in MuZero we are learning the representation states implicitly through the backward path. We don't. If you observe here, we have no constraint on the states. So the latent space, they are like how can I say? They are learned implicitly with no loss. And this is actually disadvantaged in MuZero, and efficient zero came exactly to solve the problem. It has added specific constraints on states to be consistent as a whole. MuZero was one of the most interesting algorithms. It has extended AlphaZero to operate in complex environments in the first place. Yet in the second place, it was not perfect. They say it suffers from instability. It suffers from simple efficiency problem because in here we are not imposing any constraint on the states, so it will take millions and millions of steps in order to converge. And efficient zero, another algorithm, came and added a specific loss or specific constraints in the loss. It's like an, the current state of the art model-based reinforcement learning algorithms. Actually, they use we can call it the latent space is like that imaginary space. It's like the dream. The RL agents. If I summarize its intuition, they dream in an imaginary world. They like plan in their dreams, and then they pick the most promising actions in that dream, and they win games, um, and they learn iteratively. It was impossible to cover these algorithms today because we have 4 or 5 dreamer algorithms, each one with its advantages and disadvantages. We can have them in future reading sessions, inshallah, why not? And yeah, dream, plan, and conquer. That's model-based reinforcement learning. What we do in Monte Carlo Tree Search, we are dreaming imaginary scenarios, just like we do when we think in chess games about different strategies. Then, according to those strategies, to those dreams, we plan optimal action making, and then we conquer. We conquer games we conquer problems, and yeah, that's model-based reinforcement learning session. If you have any question, please feel free to ask. I'm here, I'm available, and thank you so much for attending. Thank you everyone for staying here. Thank you for attending. And you can turn off the record. And thank you for taking care of this. And by the way, I will share all the resources